Hello everyone, and welcome to this video lecture on ideal basic circuit element. The ideal basic circuit element is not a physically realizable circuit element. Rather, it is an ideal circuit theory abstraction that is used to model actual components and system. The ideal in the name refers to the fact that this element can be described mathematically just in terms of voltage and current. Basic refers to the fact that the element cannot be further subdivided or reduced into simpler elements. And the circuit element refers to the fact that it is a two-terminal device. The ideal basic circuit element has two circuit representations which are commonly used. It is represented as a blank rectangle or square box with two terminals. Since an ideal basic circuit element is completely described by current and voltage, it is important to understand the current and voltage conventions. Let us examine the current first. Recall that the current is always measured flowing in or through a circuit element, and current flow has a direction associated with it. In the symbol for the ideal basic circuit element, the arrow denotes the direction of the conventional current I. Thus, in this case, conventional current or positive charge is entering terminal 1 and leaving terminal 2. Recall that the direction of electronic current is opposite to the direction of conventional current. Hence, in this case, electrons are entering terminal 2 and leaving terminal 1. Next, let us examine the voltage. Recall that voltage is always measured between two terminals. We use the plus and the minus sign to define the voltage polarity. Thus, in this case, we are looking at the voltage at the terminal marked plus with respect to the terminal marked minus. Finally, we are also interested in the power associated with an ideal basic circuit element. To do this, we need to apply the passive sign convention. The passive sign convention states that when the current enters through the positive terminal of an element, we use the power formula with a plus sign. Otherwise, we use the power formula with the negative sign. Deciding the sign of the power formula is the first step. The next step is to substitute the values of V and I, and these values of V and I could be positive or negative. If the final answer is positive, we say that the element is absorbing power, or equivalently, power is being delivered to the element. Similarly, if the final answer comes out negative, we say that the element is supplying power, or equivalently, power is being extracted from the element. In ideal basic circuit element problems, there are four possible ways to assign voltage polarity and current directions. Further, for any given reference polarity and current direction, the values of V and I can be positive or negative. Let us see some numerical examples how to work out the voltage and current relationships and power associated with an ideal basic circuit element. Consider the first example with given values as shown. First, let us take a look at the current. We can see that a plus 2 amp current is entering the terminal 1, and the direction of the conventional current flow is from terminal 1 to terminal 2. Thus, in this case, positive charge is flowing from terminal 1 to terminal 2. Since the direction of electronic current is opposite to the direction of the conventional current, we can see that in this case, negative charge is flowing from terminal 2 to terminal 1. Next, let's have a look at the voltage. Recall that the voltage is defined as voltage at the terminal marked plus with respect to the terminal marked minus. Thus, in this case, we can write V is equal to voltage at the terminal marked plus, which is terminal 1, minus voltage at the terminal marked negative, which is V2. Then we substitute the values. We have minus 4 is equal to V1 minus V2. Moving V1 to this side, we have minus 4 minus V1 is equal to minus V2, which implies, since the negative sign cancels, we get V2 is V1 plus 4. Using the definition of the voltage, once we arrive at this relationship, we can then determine the voltage rise and voltage drop relationships. In this case, we can see that voltage at terminal 2 is voltage at terminal 1 plus 4 volts. Thus, voltage at terminal 2 is higher than voltage at terminal 1. Therefore, when we go from terminal 1 to terminal 2, there is a voltage rise. And when we go from terminal 2 to terminal 1, there is a voltage drop. Finally, let's have a look at the power. The first thing to do is to decide the sign of the power formula. To do this, we apply the passive sign convention. The conventional current is entering the terminal marked plus. Therefore, we use the power formula with a plus sign. The next step is to substitute values. So this gives minus 4 times 2 is equal to minus 8 watts. We can see that the final answer is negative. This means that element is supplying power, or in other words, power is being extracted from this circuit element. Let us consider a second example with voltage and current as shown. First, let us have a look at the current. In this case, the current is minus 6 amps flowing in this direction. This is equivalent to 6 amp current plus 6 amp current flowing in this direction. Now we can see that the conventional current is entering the terminal marked 2 and leaving the terminal marked 1. Therefore, positive charge is flowing from terminal 2 to terminal 1. Since the direction of the electronic current is opposite to the direction of the conventional current, in this case, negative charge is flowing from terminal 1 to terminal 2. Next, let's look at the voltage. The voltage V is defined as voltage at the positive terminal with respect to the voltage at the negative terminal. Therefore, in this case, V is V2 minus V1. This has a value 2 volt. So 2 is equal to V2 minus V1. And we can rearrange this to show that V2 is V1 plus 2. This relationship now allows us to determine the voltage rise and voltage drop between the terminals. we can see that voltage at terminal 2 is higher than voltage at terminal 1. Therefore, there is a voltage rise when we go from terminal 1 to 2, and there is a voltage drop if we go from terminal 2 to terminal 1. Finally, let's examine the power. The first step is to decide the sign of the power formula using passive sign convention. We can see that in this case, conventional current having this magnitude is entering the terminal marked minus. Therefore, we write the power formula with a minus sign. And next we substitute the values. So this gives minus 2 times minus 6. And this is equal to plus 12 watts. Since the final answer is positive, we can say that element is absorbing power, or power is being delivered to this circuit element. This last example considers interconnection of two ideal basic circuit elements. Such an interconnection captures many practical cases of interest. For example, a smartphone B connected to a laptop A for charging, or car A charging flat battery of car B, or power station A connected to power station B. In such cases, we are typically interested in the magnitude and direction of power flow. Suppose V and I have values as shown. For circuit element A, we can determine the power as power is V times I. We use the passive sign convention to decide the sign of the power formula. Since the conventional current I is entering the terminal marked minus, so this direction means the conventional current is entering terminal A at the terminal marked minus. We use the power formula with a minus sign, and then we substitute values. So this is 500 kilo times 1800, which gives minus 900 megawatt. For circuit element B, power is voltage times the current. We can see that the conventional current is entering the terminal marked plus. Therefore, we use the power formula with a plus sign and then substitute values. And this gives plus 900 megawatts. We can see that for circuit element A, the power is negative. Therefore, circuit element A is supplying power, and circuit element B is absorbing power. Therefore, the direction of power flow is from circuit element A to B. In summary, the ideal basic circuit element is an important circuit theory abstraction. This slide summarizes the passive sign convention applied to the ideal basic circuit element. When the conventional current is entering the terminal marked plus, we use the power formula with a positive sign. Otherwise, we use the power formula with a negative sign. Thank you for watching this video.